let us start here. So the temperature Boltzmann distribution curve. Okay, first of all, right, looking at this 2013 section 2, right, module 2, with the aid of appropriate Boltzmann distribution curves using the axes provided on page 12, describe the effects, right, of each of the following reaction rates, or of each of the following on reaction rates. I spoke about this before, and we're going to be using this. So how does temperature change? Let's go. We have a general cutoff point, a general energies of activation energy, and we have one temperature here. Let's call that temperature T1. Let's assign a random temperature T1 to be 25 degrees Celsius, right? So that's just a regular temperature there. What happens when we increase the temperature now? If we increase the temperature, we're going to end up with something like this, right? T2 is going to be a higher temperature. It's going to be T2 is going to be greater than 25 degrees Celsius. Let's just say 40 degrees Celsius, right? So I think I should draw the lines a little bit better so I can explain a little bit better. Let me draw it a little bit better real quick. But you guys need to know how to provide a Boltzmann distribution curve at this level and beyond. Alright? Right? And the number of molecules now with the sufficient kinetic energy will be higher at T2 than at T1. Right? And that is because when we have our temperature at 25 degrees Celsius T1, right, there's going to be a certain amount of molecules that have sufficient energy for successful collisions, meaning that particles are going to be collided, right? They're going to collide, but they're not going to be colliding at sufficient energies, so they're not going to be successful collisions. Successful bombardments are not going to be taking place. Only the shaded blue area here, right? Only those amount of molecules, those number of molecules will have sufficient energy at 25 degrees Celsius. But if we increase rather the temperature to T2, let's say 40 degrees Celsius, we have more molecules at this higher temperature that has sufficient energy to result in sufficient collisions. Therefore, at higher temperatures, the rate of reaction increases. Boltzmann distribution curve. So you should be able to explain that. All right? Everybody fine with that? If you're okay with the information here, you can drop a 1 in the chat, or you can tell me that everything is fine, and if everything is not fine, ask a question. All right? So this is how temperature looks. With a catalyst now, right? With a catalyst now, we know the temperature is not changing. Lovely. So the temperature now, it's not changing. So let's look at this, right? If we have an initial activation energy here, right? Remember the kinetic energy is increasing this way. Let's say that this energy is the first activation energy, right? So EA1, the first activation energy, right? What catalysts do? Catalysts change, well, not really change. They create an alternate pathway, allowing for more successful collisions, especially via orientation. So it helps with that. It decreases the activation energy of the system. So here, let's use that, EA2. So at EA2, all of these molecules will have sufficient energy, right? Which would be way more than if it would just be here. So EA1 is obviously no catalyst. So no catalyst, right? And then EA2 now would be with a catalyst. So EA2 be with catalyst, right? With a catalyst. So hopefully that makes sense. Everybody okay with that now? with would be with catalyst. All right. So that should make sense. Okay. So that is the first part of our question here for 2013 that every man and woman and person should be able to do. All right. Hold on. Let me. Why is this increasing that much? Where am I supposed to be on this paper? Give me a moment. Let me find my question. But are there any questions though? Any questions though? All right. Those seem like there seem to be any questions. The values of initial rates measured for the reaction below are recorded in table 3. So we have a thiosulfate and iodine here. All right. So here the reaction rates are given. Use the information in the table to deduce the rate equation and calculate the overall order of the reaction. Right? How do we do this now? Somebody step up, please. How? In order to find the rate of equation and the order of the reaction will go hand in hand. So what do we want to do first? What do we want to do? Do you want to find the order of reaction, overall reaction first, and then use the rate, and derive the rate equation from that? Because the rate equations correspond to different orders of reaction. Now, go ahead. Never heard what you said.
So find the order first.
Okay, so let's say that now. Let's find the order first. How do we find the order of reaction from this data? The overall order of reaction, by the way. So in order to find the overall order of
So we'd
reaction,
have to find.
go ahead.
So we'd have to find the order of reaction for the S2O8 2 minus ion, and then the order of reaction for the iodine
The iodide ion. All
ion,
right.
iodine ion.
All right, so that's fine. All right, the iodide ion. All right, so lovely. So the order of reaction with respect to this molecule, that is what we're doing first. How do we do that?
We have to look on the table where iodine is constant.
Okay.
So that would be 2 and 3.
Oh, okay.
And
You're
then
using 2 and 3 and not 1 and 4. Okay, let's use 2 and 3. All right. Okay, so I'm gonna ask you now. I want you to continue, but I'm gonna ask you why we use those two. Hold on, why the screen went? I'm not sure why this always happens when I'm sharing page.
Excuse me, sir. Can stop presenting and represent.
No, it should be back now. When it goes black for you, it goes black for me as well. I'm not sure why it does that. It should be up now. You can see it now. Are we fine now?
Yes, sir.
Lovely. So the person who was saying
yes, sir.
now, right, that we use these two. Why we use these two? Why we use 2 and 3 for iodine remaining constant? It's just because you wanted. Could you use 1 and 4 as well? Is that just a question? Could we use 1 and 4 as well?
Yeah.
Okay, but you chose to use 2 and 4, right? All right, so 2 and 3. What would the next now?
So next we would find out like if 2 and 3 is multiplying by 2
Mm-hmm.
and the rate is also multiplying by 2, then it will be first order.
All right, let's see what you're saying. You're saying that if I times this by 2, right? Hold on. What are we looking at? What is multiplying? Is the rate we're looking at, right? Are we looking at the rate or are we looking at the concentration? We have to see how the concentration changes and relate that to how the rate changes, right? So how does this concentration change here?
Yeah.
How does the concentration change here? Hello? It doubles, right?
No, sir.
Wait, let's see. If we take 0.075, right, and we times that by 2, don't we get 0.015? Okay, it doubles from 3
So
to
it's
2.
half.
Okay, so it halves, right? So it's either if it halves going in 2 to 3 direction, right? And it doubles when it's going up, right? Wouldn't it just be the opposite? Let's see if we get 0.15. If we divide that by 2, we should get 0.0075. And if we have 0.075, and if we have 0.075 and we times by 2, we must get back 0.15, right? So we're seeing that it's what we're having is doubling, right? Because we use it in concept of doubling, right? If it halves as it changes in one direction, it will double going the opposite direction, right? So what's happening to the rates now? The thing is now with the rates, I always look at it in concept
The
of
rate
increase.
also double.
The rate also doubles. So if the concentration of thiosulfate doubles and the rate also doubles, what reaction is this? What order?
First order reaction.
So the reaction is first order with respect to that unit. Everybody's fine with that? Any questions? Okay, everything is fine. Oh, lovely. So with iodine now, and the iodide ion, let's look at that now. Which two equations, which two reactions or two experiments are we using to find the iodide now? But go ahead.
Experiment 1 and 2.
So using experiment 1 and 2. All right. So let's use experiment 1 and 2. So we have this remaining the same and iodide changing. All right. So what's happening here now? Is it doubling? 0.25 times 2 is what? 0.5, right? So that's doubling. Is this doubling as well? What's that change?
So for the concentration is doubling, but the rate is quadrupling. So
Rate
it will be second.
second order.
Yeah.
All right. The rate is quadrupling, so it is second order.
No, it's quadrupling.
Hmm? That's fine. So the rate is increasing by 4, right? So its rate is quadrupling there. All right. So does everybody agree that this reaction is first order with respect to the sulfur ion, right? That sulfur containing ion, right? And second order with respect to the iodide ion. Everybody agrees? All right. So we're agreeing. So what is the overall order of the reaction now? What's the overall order?
Third.
Interesting. All right.
Third order.
Third order. All right. So good look at it, right? So it's 1 plus 2 equal 3. It is third order. So it's third order. All right. So we just add up the orders, right, to get the overall order, right? So what's happening now? If we deduce the rate equation, what would be the rate equation now? Rate now.
Rate equals K
Okay, rate equals K.
times S2O8 2 minus
The concentration, right?
in square brackets.
Okay, so square brackets denote concentration. Wait, hold on, let me just
Here
shift the screen a little bit.
times iodine raised to the second power.
Alright, so S2O8 2 negative raised to the first power, which would we just leave it, right? It's the first power, and now that's being times by iodine specifically, right? What am I doing? Why I write that 2 up there? Alright, let's see. Iodine, right? Squared, right? So we have that, and the overall order is third order, right? So that is the rate equation, right? So calculate the rate constant now. What would be the rate constant? So if the equation, right, rate is equal to K is okay, so if we have that rate equation up here, right? This rate equation, right? Let's go up here and look back at the rate equation. So how do we get the rate constant K? I would recommend transposing, right? Guys, ladies and gentlemen, talk to me. Do we transpose to find K? Go ahead, Shanique. You raised your hand, but isn't the 2 supposed to be outside? Okay, as it relates to the rate law, right? You're asking if the 2 is supposed to be outside. Okay. So is the 2 supposed to be outside for that there?
Yeah,
Okay, so you said yes. Alright. So if we have the rate law for that, the 2 is supposed to be outside, that's what we're saying. Alright, interesting. Alright, so is the 2 supposed to be there overall? Because it begs the question, is the 2 supposed to be there overall? The 2 doesn't have to be there. The 2 we don't, in this case, we wouldn't care about the stoichiometric thing, coefficient. It's not raised, we don't use the stoichiometric coefficient. This is not Kc or anything like that. This is just rates, right? So looking at it with respect to different ions present, we don't necessarily have to write in 2 in front of it or anything like that, alright? So thanks for reminding me of that, right? But as it relates to this now, we don't necessarily have to do that. I'm not sure if anybody has any objections as relates to that, but we don't necessarily have to write that coefficient out there, alright? For this now, what we'll do is just select a random experiment and use those values to get K, right? So we should be able to use any experiment there. And in this case, K would be equal to what? If we transpose, what would K be equal to? What would K be equal to? K would be equal to the rate, right? The rate divided by, right, our reactants, right? concentration of our reactants. 2 minus, should be 2 minus, and then we have iodine. All right, this should be fine, right? Everybody's fine with that? Guys, are we fine with that?
Yeah.
Okay, so when we plug in the values, we're supposed to get a rate constant K, right? So in the interest of time, I'll just plug everything into the calculator at once, and you guys should be able to use any of these experiments, right? I just tend to go with experiment 1 because it's the first experiment. All right, so I'm just going to plug in all the variables at once. Like 4 times 10 to the power of negative 5 divided by 1 times 5. What is the unit of K that we got? What is the value that we're getting? Waiting on the values. I'm just doing the second experiment as we speak, so I can make sure that it should theoretically be the same thing. For experiment 1, 0.15. Oh, the rate is different. All right, what are the values we're getting? Hello? What?
5.8 times 10 to the minus 6.
Which experiment did you use?
The first one.
5.8. Okay. 4 times 10 to the negative 6th power, negative 5th power. We divide it by 0.15 times 0.25, and your value is 5 point something. Is somebody calculating something incorrectly? Because I have a feeling that I made my calculation maybe interesting enough. Let's see. Let me see if I can figure out what you did to get that value. All right, so you should be able to plug in the value to get the unit of K. Well, to get K specifically. I want to see everybody else's values. What are the values that everybody else is getting? What are they? Are you guys attempting the questions?
So I check the chart.
All right. Let me just check the chart. Okay, 3.73 going down. All right, so the value that you got is 1.86 times 10 to the negative 4. person would
Oh
say,
no, I got 5.8 times 10 to the minus 6.
okay, I'm not sure where that value is coming from. Could you recheck the calculation? Because if I plug in this value, what I'm getting is 3.733 times 10 to negative 4, right? Which is the same thing that somebody else got in the chat. I'm not sure how you get 5 and how you get negative 6 overall. That is my huge concern, how we got 10 to the negative 6 as our answer. Using experiment 1 to get that, so this divided by this product of these two should give you 3.733 times 10 to the negative 4th power the rate constant k over here should give 3.733 times 10 to the negative 4th power. And the rate constant, though, since you have something like that, with your rate constant, what would be the unit of k for a third order reaction? Okay, hold on, guys. I think there's one thing I was missing. With calculating your reaction K specifically, right? The entire reaction K. Hold on, never mind, that should be fine. If you have something to second order, when you're calculating K, you square the value, right? That may be one thing that I forgot to put there. Right, so in that case, if it's going to be squaring the value, you have to square the 0.25. Right, so that may be the issue that I had here. So let me actually just square that value right now. Let me square it to see if I'll get the same value that this person is having. Alright, so I'm gonna times this value now by the 0.25 squared, and we should be able to get value that makes sense. So 1.4 times 10, let me write it out.
So check the chat.
Let me see the chat for all of them. All right, so that means that the squaring, you squared, right? So that is the issue there. Okay, 1.4 times 10 to the power of negative 5, and we should be dividing it with the first reaction. It should be 0.15, right? Should be 0.15 times 0.25 squared, right? And you should get that a value, right? And let me just get that value to confirm that that answer is the right answer there. That would be 0.15, and then we times 0.25 squared. And the answer I get is that 1.49 times 10 to the negative 3. All right, so the rates constant k is actually that. So I forgot to square, my bad. All right, so if we square, we should be getting that. So let me see if I can erase the value that I had up here. So it wouldn't be this value. All right. So if we erase that, we should be getting the 1.49 times 10 to the negative third power. That's how we should be getting. All right. So if we're supposed to be getting that now, what is the units of K? So this is equal to K, and well, K is equal to that, which is equal to the 1.49 times 10.
Sir, can you go back up to the table, please?
Give me one moment. Times 10 to the power of negative 3. Alright, so going up back to the table. Here's the table. Alright, so if we're using these, right, remember the rate law says that iodine would be squared because it's second order. So we square all the iodine values when we're doing it. I should be able to get the 1.49 times 10 to the negative third power. Alright, so when we do it like that now, we're supposed to get that, and what would be the units of K? What would be the unit of K? So I did this before, explained this before. So let's have a go at reducing the units of K. So if we have more, well, rate is in mole per dm cube, right? So rate is in, well, mole per dm cube per second. So it's mole per dm cube per second. All right, all divided by mole squared, right? Dm cube squared. So what's gonna basically happen in this? This is essentially cubing the thing, right? So if you're gonna have that, right, we're gonna have what here, mole squared. Let me just do it like this: mole squared dm to the negative sixth power, right? And then we're gonna be timesing it by mole dm cube. Right? So we have something like that, right? On the denominator, what we're gonna end up with is what? Mole cube, right? Gonna end up with mole cube dm to the negative ninth power, right? Divided by, right, our original mole per dm cube per second. Per second, right? And then what's gonna happen here, we're gonna cancel out, and what we're gonna end up with here now, we're gonna cancel the mole, we're gonna get mole squared down here. So this is gonna be mole squared. We're gonna cancel dm cube, we're gonna get dm to the negative 6 down here. So it's gonna be negative 6, right? And if we bring it up to the numerator, what we're gonna have is per mole cube, well, per mole squared rather, right? So mole to the power of negative 2, right? dm to the power of positive 6 times seconds to the power of, well, negative 1. Hopefully that makes sense. So dm to the power of, well, this would be positive 6. And then you're gonna have seconds, well, we'd have per second. Right? And those would be the units that we have there. Alright, so we'll have that like that. So when you bring these up to the numerator, you're gonna have the exponent. Simple, right? So that's what we have there. Okay, so the unit of K now, right, is generally just mole per squared dm to the 6 per second. Is answer. Alright. The last thing, initial rate of reaction. right, when the concentration of this is like that, and concentration of this is this, right? How will you guys calculate this? All you do is use the general rate equation again, plugging these values along with k to find the rate. Make sense? So you're going to plug in this value, you're going to plug in this value, right, squared, and you're going to plug in the k that we just calculated in order to get initial rate. So rate is equal to this k here, right, times, right, these concentrations, the product of these concentrations here. Everybody's fine with that? Okay, so we're assuming that everybody's fine with that. So that would be what we're gonna do for that question there. All right. I don't. Is it necessary to actually do it? Go to the calculations to do it, because all we're gonna be doing actually is just plugging in values, right? So what we're saying is that the k, the well r, right, the rate here now, which would technically be r naught, right, would be equal to 1.49 times 10, or 49 times 10 to the negative third power, right, which that would be k, and we're gonna times that by the 0.13, and we're gonna times that now by the 0.32, and we're gonna square that, and we're gonna get the rate there. All right, so I don't think we need to go through that. So is everything there fine? Everything's fine? Ladies and gentlemen, is everything fine? All right, so that is the end of this rate section here.